Okay, next talk is Quasilinear Time List Decodable Codes for Space-Bounded Channels by Swastik, Kopparty, Ronen, Shaltiel, and Yad Silbak. And Yad, give the talk.
Okay, so I'm going to talk about list decodable codes, and specifically for some bounded channels. Okay. So let's describe our setup on what we mean by list decoding. So generally speaking, we have some message M that we wish to send to another party. And the problem is that we send it through some noisy channel. Okay? So the way to deal with this, of course, is to encode our message M through some encoding scheme, and then send it through the channel, and hope that the decoder is able to recover the original message using its decoding function, right? Now, here, what we mean by recover is, of course, produce a list of at least, or at most some L constant candidates that at least one of them is the original message. Okay. Now, the rate of the code, or how good the code is measured by the ratio between the message and the encoding. Okay. Now, usually, whenever we talk about list decoding, we actually refer to the Hamming setup, right? So what are Hamming channels? These are channels that are very powerful, right? They can change any PN positions in the code word, and they are a very powerful adversary, right? So the channel can choose any PN positions, and they can change them. And for such channels, of course, it's natural to ask if we can actually produce the best possible code, right? So can we have the best optimal rate for these kinds of channels? And existentially, we know that such channels exist, right? So it's actually quite easy to prove that, in fact, they do exist. But this is not really what we want, right? What we want is an explicit construction that achieves the optimal rate. And today, even after considerable effort, this is still an open problem. We don't know. Okay? So unfortunately, we don't have any explicit constructions as of yet. Okay? But in a parallel universe, right, there exists a body of work, a famous body of work that does achieve this optimal rate, right? But not for Hamming channels. And this, of course, is the Shannon channels, right? And the most famous of which is, of course, the binary symmetric channels. Okay. So binary symmetric channels are very weak because they don't even look at the code word itself, right? They independently flip every candidate, every bit with probability p, and actually the channel itself doesn't look at the encoding, right? It's independent of it. And fortunately, as I said before, for this kind of families, we do have efficient explicit constructions with optimal rate. So now we have these two spectrums, right? On the one hand, we have a very powerful adversary that is all powerful in a sense, and on the other, we have a very weak channel, right? Very weak families of channels. And it's quite natural to ask if there is something in the middle. Can we consider an intermediate concept, right? In which the channel is still an adversary, but it's not an all-powerful adversary. Okay? Good. So let me try to help you at least understand what I mean by this. So as I said, we want it to be an adversary. And of course, naturally, it's natural to think of a model where, let's say, we have a Hamming channel that is, let's say, computationally bounded in a sense. Okay? So in fact, Lipton already considered such families of channels where they induce at most PN errors, and they come from some non-complexity class. So you can think of time-bounded channels, and specifically for us, think about online space channels. Okay? So in this work, I'm going to talk about online space channels and efficient codes for them. Okay? Good. So let's talk about what we mean actually by online space channels. And online space channels can be modeled by the following setup, right? So you have a machine that reads the input in one pass. It's a state machine in a sense. It has its internal memory. And whenever it reads a bit, it updates its internal state, and it outputs an error. Or decides it doesn't want to output one. Okay? So in each iteration, it decides if it wants to output an error or not. Okay, so there's still a problem, though. And the problem is that even if we consider a very weak channels that do have some non-uniform advice, then it turns out that if we have a code that is good against such channels, this code is actually good against Hamming channels. Because in the worst case notion of coding, it only takes one code to be in the wrong place to actually fail, right? So if we have some encoding, we have some point y that is like centered around some ball that has too many code words. So a non-uniform, a very weak non-uniform adversary can actually push this code word toward this ball, and we were not able to recover, right? So a very weak non-uniform channel can actually kill us. But there's still hope, and this hope is what we refer to as stochastic codes. And stochastic codes have random encoding or randomized encoding and are expected to succeed only with high probability. Okay, so let me now restate our setup of list decoding, but this time from the point of view of stochastic codes. Okay, so again, list decoding from the point of view of stochastic codes. Again, we have a message M we want to encode, but this time we give the encoding function some extra randomness R. Okay, so the encoding function now takes this randomness and can use it. Again, we send it through the channel that this time is like it's chosen from this bounded family. And again, we hope that the decoder is able to recover the original message, right? And this is list decoding, so we want that with high probability, one of the messages that was recovered is the original message. Okay. Now, note here crucially that both the decoder and the channel don't receive the randomness, right? So this is not there is no prior setup where they share some information and right, etc. So this is a very lightweight setup. Okay. Good. And of course, the rate remains to be M over Z because M is the information we're sending, right? And again, this is the formal definition if it helps someone or anyone. Okay, so let's go over it slowly. So we have an encoding and decoding, and we say that this encoding and decoding are stochastic codes that are good if for every M and for every C in this class of bounded space channels, the decoding succeeds with high probability over the choice of R. Okay? Good. And of course, the code is explicit if encoding and decoding run in polytime. So what do we know about these families of codes? Okay. So in a great work by Goswami and Smith, they showed that if we consider that we can actually have explicit construction for stochastic codes with optimal rate, if we consider additive channels. Now, additive channels, you can think of them as non-uniform channels that are like have essentially zero space. They don't do any computation, but they are adversarial in a sense that they have this non-uniform advice they can use. And they also showed that this is the same paper that for every constant C, there exists a Monte Carlo explicit construction that achieves the optimal rate for the class of C log n space. Now, what I mean by Monte Carlo here is that there is a pre-processing stage in which the encoding and decoding share them public coins. Now, these coins can later be published, and the channel can have access to them, but this is not important. Okay. And in a follow-up work we had later, we showed that actually this is not needed, and we can actually have explicit construction with optimal rate for space that is C log n without any such setup. Okay. But there is a major drawback or a major weakness of all of these results is that actually the runtime of the encoding and decoding was really dependent on the size of S. So whenever S was large, right? So if you choose like the constants to be large, then this meant like a very bad runtime, right? So if you take C to be too large, then you get a abysmal runtime. Okay. So what do we do in this work? We showed that we are able to achieve least decodable stochastic codes with optimal rate for any order space, and I will say a few things about it later. And this space is quite large, right? So it's for n to the omega of 1, quite larger than log of n. And crucially here, that we are able to achieve encoding and decoding that run in almost linear time. So not only is it not dependent on the space, it's also quite good. Okay. And the second result states that if you don't really care for the runtime, but you're willing to live with some fixed polynomial runtime, then you're able to achieve a much higher space, and you can actually have space that is n over polylog n. Okay? And this result only applies for a small piece, not all the range. Okay. So this is interesting, or you can think of, you may ask yourself why this is important, right? So in a sense, all the channels that are studied in information theory, for example, binary symmetric channels, burst channels, and etc., are all can be implemented by small space, right? So in a sense, you can think of this result as being a unifying work that says all of these results or all of these channels can actually be implemented or can actually achieve the optimal rate and can actually, we can actually do so in a very efficient manner, okay? Good. So in the time I have left, I'm going to show you some of the cute constructions we have or cute component we have. And this is an inner component. If I have time, I'll show how we're going to use it. But for now, like, just note that this is an inner component, and hopefully I'll get to why it's important. Okay? So we want a code that has these two properties. First of all, it should be explicit, or it should be an explicit list decoding, and should be able to recover from almost half errors. This is the first one. And the second property we need is that we need this code to be a linear code with with a quite large dual distance. Okay, so for everyone, like I hope everyone knows what the dual distance is, but it's the distance of the dual code. Okay. So who are the usual suspects? Right, we want such a code, and we want a huge dual distance, and we want it to be able to recover from quite a lot of errors. So of course, the first candidate you may think about is the dual BCH code. Okay. So what do we know of these codes? We know, for example, that they have a huge distance, right? Almost half. We also know that their dual distance is excellent, right? So what's the problem? Well, fortunately, we don't have any explicit decoding algorithm. So we don't have any explicit decoding algorithms for such codes. Okay, so this is a problem, and we scrap this. So another candidate. Here's another one. Let's have a Reed-Solomon concatenated with some inner code. Well, that's good because we have explicit list decoding for such algorithms, right? By the amazing results of Sudan and Goswami. And of course, the problem here is because of the inner codes, they completely destroy the dual rate, right? So we can do this. We can use them. Okay. So what do we do in this work? In this work, we actually show that good old Reed-Solomon codes viewed as or seen as binary works, right? So nothing fancy, it doesn't need anything. And you may actually think this is very suspicious, and in fact it is. So let me state it more formally. So suppose n is of power of 2, and we have some encoding of Reed-Solomon from k symbol to n symbols. So if we view this encoding as just being a binary encoding, right? So from k log n to n log n, then we claim that for k that is sufficiently small, what we have here, we get a code that satisfies the above two qualities. Okay? So, okay, and we call such codes, of course, raw Reed-Solomon codes. So these kinds of codes, we call them raw Reed-Solomon codes. Okay. So I want to note here that, first of all, the natural argument for distance, or for distance, only gives us 1 over log n, right? And this is quite bad. So if you interpret every symbol as being just a binary representation, this is horrendous. And another thing to note here is that the R, or the rate here, is quite small, right? It's a very small rate. But since this is an internal component in our construction, we're able to live with it because it encodes a very little information. Okay? Good. So let's show, with the time I have left, let me show you why this is true. Or let me give you an intuition why this is true. So let's state our standard interpretation of what Reed-Solomon code is. So as I said before, it's a Reed-Solomon, in a sense, concatenated with an identity, right? This is what we have. So we have a message, and we encode it. We get a lot of symbols. Not all of these symbols are over some large alphabet. And we use the identity to actually write them as bits. Okay. Now, if we are to consider or to rearrange this code word and consider every ith bit in all of the symbols and put them all together, right? Bundle them all together, then it turns out, surprisingly so, that every such bundle, right? Every such gathering it actually makes up a dual BCH code. So why is this good, right? This is good because actually we know that the distance for dual BCH code is around half, right? So if each one of these bundles is a code word for is a code word for dual BCH code, then we are able to retain our distance. Okay? So if we're able to show that all of them are a non-zero BCH code words, then we get a high rate. Okay? We get a large distance. So this gives us the distance. And actually, like I cheated a little because it's easier to see this is true whenever you only take a Reed-Solomon code that only has odd monomials. But this is also true for general Reed-Solomon codes, but it's quite more involved. Okay? We actually reduced to this setup. So we had first properties we got is the distance. So how are we going to achieve the list decoding? So this is quite interesting because we can actually think of the inner code, the identity, as being a code, right? So now we can list decode this code. Now because if this code this is not really a code, right? This is a code that has distance 1, right? So we'll get huge lists, but this is fine because we have explicit algorithms for list recovery by Goswami and Smith that actually can deal with this. So we have an explicit algorithms by Goswami and Smith, by Sudan and Goswami, that are actually able to explicitly recover this list. And the crucial part is, and this is where it becomes interesting, is because we have distance, right? Because we get that distance from the dual BCH codes representation, the Johnson bounds tells us that if you have a code was list recovered and has a lot of distance, then this means that the list you get in the end is quite small. Okay? So we are able to list decode in an efficient manner. Okay? So we get a code that is, so let me recap. We get a code that is that has a dual distance or a huge dual distance that it inherits from the Reed-Solomon, right? So it inherits from Reed-Solomon. It has polytime encoding and polytime list decoding with a small list. Okay. Good. So how are we going to use this? Why is this useful? Well, it turns out that there is a component in both prior results that actually had the following properties. And this component is the following. It's a code that has pseudorandom property and the list decoding property. And the first property means that if you take take x with or you encode x with some uniform string, then what you get is something that is pseudorandom from the point of view of some space channel. So any online space bounded channel will think that this is pseudorandom. And the second property is that for every x and r, if we and error pattern e that is not that is small weight, that we are able to recover. Okay. So previous results all showed that existence of such codes, and they resorted to brute force to get them. And this actually meant that our runtime actually very much dependent on the size of S. Okay. So in this work, we show the following approach. We show that actually to get such a code with these two properties, pseudo-randomness and the list decodability, we actually can use our raw Reed-Solomon codes and simply add some noise to them. So this is quite surprising because this doesn't seem like a working strategy, right? So let's see why this is true. It's true because if you think about it, as I said before, this code is linear and has dual distance, or a huge dual distance. So we can actually now use a result by Violet and Lee and Forbes and Kelly that actually showed that T-wise independence or L-wise independence plus some noise is actually able to full space. So the dual distance here translates to L-wise independence. And as I said before, if we actually put the R here to be random, then we get independence. At the same time, because this is a code, right? Because this is a code, the fact that we added to this code word small noise doesn't really hurt us that much, right? So we're still able to recover. It doesn't hurt us. So putting everything together, we actually get this code, and this, together with some additional more ideas, is what enables our construction. Okay? Okay, so let me recap everything that, that we did. So in this result, if you want to take something home, is this. Like, we actually, we showed that we are able to have least decodable stochastic code that are optimal for space that is considerably larger than before. Specifically, you can get even quasi-linear time encoding and decoding for S that is n to the omega of 1. And if you're willing to settle for polytime decoding and encoding, then you can actually have space that is n over polylog n. And what about open problems? Well, the first one is, can we get a unique decoding? Well, subsequent work we have showed that we actually can do this. It wasn't easy, but we actually proved that we are able to do this for P that is smaller than 1 over 8. But we still don't know anything about the region between 1 over 8 and 1 over 4. And Grossman and Smith actually showed that we can't actually have unique decoding for P greater than 1 over 4. Okay. And the second question is, can we have encoding and decoding that run in linear time? And this is we don't have any idea because our construction really heavily relies on some tools that like have n log n built in them. Okay. So that's it. Thank you, everyone.
Other questions? Okay, let's thank the speaker again then.
Thank you.